What specific problem does your proposed model merging method aim to solve, particularly in the context of compositional generalization? Could you explain why this focus represents a more realistic motivation compared to held-in-task performance?
Our proposed model merging method aims to solve the problem of enabling compositional generalization, which allows a merged model to combine capabilities from different constituent models to tackle new tasks that require skills not present in any individual model. This focus on compositional generalization is more realistic than merely improving held-in-task performance because it reflects typical use cases of merging, such as combining styles in image generation or enabling zero-shot generalization in language models. While held-in-task performance is important, it often does not capture the true utility of merging, as users typically seek to leverage the diverse capabilities of multiple models to address novel tasks. Our work emphasizes that the primary benefit of merging lies in unlocking new capabilities and applications, rather than just retaining performance on tasks the original models were trained on. This perspective aligns with the practical motivations for model merging, as it addresses the need for models that can generalize beyond their training data.
Can you explain how the proposed model merging algorithm works? Please illustrate the steps involved, especially how the constituent model's parameters are combined and how the new model is constructed.
The proposed model merging algorithm combines parameters from multiple constituent models to create a new merged model that retains the capabilities of the individual models. The process begins by selecting the constituent models denoted as theta_i for I in 1 L.m, which are typically fine-tuned on different datasets. The merging methods vary, but one common approach is simple averaging, where the parameters of the merged model, theta_m, are computed as the element-wise average of the constituent model parameters. Theta_m equals frac1, m sum_i theta_i. More sophisticated methods such as task arithmetic involve constructing a task vector for each model by subtracting the base model parameters, theta_p, from the constituent model parameters and then combining these task vectors with a scaling hyperparameter, lambda, to form the merged model. Theta_m equals theta_p plus lambda sum_i tau_i. Other methods like Fisher merging and regmean utilize statistical approaches to optimize the merging process, focusing on maximizing joint posterior distributions or minimizing distances between activations respectively. Ultimately, the new model is constructed by integrating these combined parameters, allowing it to generalize to new tasks while retaining the capabilities of the original models.
Could you provide a simple yet illustrative example of the model merging process as described in your paper? Walk through the key steps of your merging algorithm with this example, explaining how the intermediate results contribute to the final model.
An illustrative example of the model merging process can be seen in the task arithmetic method, which combines models fine-tuned on different tasks. Suppose we have two constituent models. Model A, fine-tuned for image classification of fruits, and Model B, fine-tuned for image classification of tools. The merging process begins by calculating the task vectors for each model, defined as tau_a equals theta_a theta_p, and tau_b equals theta_b theta_p, where theta_p is the base pre-trained model. Next, we scale the sum of these task vectors by a hyperparameter, lambda, and add it to the base model to create the merged model. Theta_m equals theta_p plus lambda, tau_a plus tau_b. This intermediate result retains the capabilities of the base model while integrating the unique features from both constituent models, ultimately enabling the merged model to classify images that require knowledge of both fruits and tools, thus achieving compositional generalization.
What are the theoretical or practical benefits you observed from using your model merging approach compared to other traditional alternatives? Have you quantified improvements in efficiency, accuracy, or scalability?
The model merging approach we explored offers several theoretical and practical benefits compared to traditional alternatives. Firstly, our findings indicate that merging can significantly enhance generalization performance, particularly in cross-domain image generation tasks, where merged models often outperform multitask training. We quantified this improvement by demonstrating that while held-in performance tends to decrease with an increasing number of merged models, generalization performance generally increases, suggesting that merging effectively expands the range of underlying capabilities. Additionally, we highlighted that methods like ties provide a favorable balance between performance and practical considerations, such as lower computational costs and fewer prerequisites, making them more applicable in real-world scenarios. Overall, our comprehensive evaluation underscores that merging methods can yield meaningful efficiency and accuracy gains, particularly in settings requiring compositional generalization, while also revealing the scalability of these methods as the number of constituent models increases.
How did you validate or test the effectiveness of your model merging methods? What datasets did you use for benchmarking? And what metrics or experimental designs were critical to demonstrate your findings?
To validate the effectiveness of our model merging methods, we conducted a rigorous evaluation focusing on both held-in performance and compositional generalization across various tasks. For benchmarking, we utilized the DomainNet dataset for cross-domain image classification and generation, which consists of 586K images across 345 classes and 6 domains. Additionally, we employed the Mount 5XL LM-Adapt model for cross-lingual natural language processing tasks, evaluating performance on 5 distinct tasks available in different languages. The critical metrics included the performance of merged models on held-in datasets versus their performance on unseen datasets requiring compositional generalization, allowing us to assess the generalization capabilities of the merged models. Our experimental design involved a hyperparameter sweep and scaling analysis, where we varied the number of constituent models merged to observe trends in performance, revealing insights into the trade-offs between held-in and generalization performance.
What were the main results achieved with your proposed method? Can you summarize specific performance metrics that highlight the improvements or unique capabilities enabled by your model merging approach?
The main results of our proposed model merging methods indicate that merging can significantly enhance generalization performance, particularly in cross-domain image generation tasks. For instance, we found that many merging methods outperformed multitask training in both held-in and generalization performance for image generation, showcasing their effectiveness in composing capabilities from different models. However, in natural language processing, we observed an anti-correlation between held-in and generalization performance, suggesting that while merging can improve generalization, it may not always retain performance on previously trained tasks. Specifically, our results showed that increasing the number of models merged generally led to improved generalization performance, although held-in performance tended to decrease, highlighting a trade-off. Overall, our findings emphasize that while merging methods like ties provide a good balance of performance and practical considerations, there remains significant room for improvement in cross-lingual generalization tasks.